The question who actually invented the stepper motor is still open to some debate, partly because original versions were not immediately known as stepper motors. However, for most engineers, ourselves included, it is largely attributed to Frank W. Woods, who patented a motor based on 5 stator coils which could be charged in various combinations to deliver step-by-step movement. There are 3 main types of stepper motors. Permanent magnet stepper. Permanent magnet motors use a permanent magnet PM in the rotor and operate on the attraction or repulsion between the rotor permanent magnet and the stator electromagnets. Variable reluctance stepper. This stepper motor uses a non-magnetized soft iron rotor. The rotor has teeth that are offset from the stator, and as we activate the windings in one particular order, the rotor moves respectively so that it has minimum gap between the stator and the teeth of the rotor. Third type is the most commonly used, hybrid synchronous stepper motor. It is the combination of the previous 2 steppers. It has permanent magnet-toothed rotor and also has a toothed stator. To show basic parts of stepper motor, we will be using most commonly used model of hybrid synchronous stepper motor. Basic parts of hybrid stepper motor are stator, rotor, bearing, and shaft. Stator has magnetic poles with small teeth. Each pole has a winding. Each winding is connected to the winding of the opposite pole so that both poles are magnetized in the same polarity when current is sent through the pair of windings. Pair of windings are shown in same color. Running a current through a given winding magnetizes the opposing pair of poles in the same polarity, i.e. north or south. The opposing pair of poles form one phase. Rotor. Rotor is made up of 3 components: rotor cup 1, rotor cup 2, and permanent magnet. The rotor is magnetized in the axial direction so that, for example, if rotor cup 1 is polarized north, rotor cup 2 will be polarized south. Bearing allows the shaft to rotate when rotor is turned. Shaft is attached to rotor and provides rotational drive for the load. Hybrid stepper motors can be made with single or double shaft. Working principle of stepper motor will be explained with 2-phase hybrid step motor who has 8 poles. With these motors you can achieve very small step angle. Let's learn working principle and explore the functionality of a typical 1.8 degrees step-sized hybrid motor. The hybrid motor has magnetized rotor with 2 steel caps, so one end of the rotor becomes the north pole and the other end becomes the south pole. The accuracy of this motor lies in the clever arrangement of the rotor and stator teeth. So firstly, let's see and understand it. Rotor has 50 teeth. To understand the stator teeth arrangement, we must first assume that the stator has 50 teeth as well. But stator has actually 2 fewer teeth than the rotor, so stator has 48 teeth. Now, let's arrange the 48 teeth into 4 group pairs like we showed in the video. Green group of teeth is half aligned with rotor. Teeth of yellow group are not aligned with the teeth of rotor. Teeth of red group are half aligned with the teeth of the rotor, and blue group are completely aligned with the teeth of the rotor. Part of the rotor which is facing you acts like the south pole. The stator coils are connected as shown in the video. As we can see, we have 2 independent coil groups. When group A is energized, blue stator windings are magnetized as shown. One pair of stator or poles become north pole and the other becomes south pole. We know through history that opposite poles attract, so they will be aligned, and the same polarity poles are not aligned. When the coil B is energized, you can see what happens to the rotor. The rotor is rotating by a small angle in order to align with the new north pole. It is clear that this angle is 1/4 of the angular pitch, so rotor is rotated by 1.8 degrees. Now we again energize set A with the opposite polarity. Again, the rotor is rotating in 1.8 degrees. So when we repeat this process, we can achieve highly accurate motion of the motor. Step angle rotation can be improved by half-stepping. It is important to know that north rotor cup teeth is placed between the south rotor cup teeth. In this way, alignment of the opposite polarity poles are guaranteed again. So, this is the working principle of high-bridge stepper motors. These are ideal for applications when precise movements and simple controls are needed. Vibration of the step motor is one problem that we must deal with. Vibration can make problems, especially at low speeds. So, when a stepper motor makes a move from one step to the next, the rotor doesn't immediately stop. Rotor actually passes the final position, then is drawn back, passes the final in the opposite direction and continues to move back and forth until it finally comes to a rest. We call this the ringing, and it occurs at every single step the motor takes. Similar to a bungee cord, the momentum carries the rotor past its stop point, then bounces back and forth until finally coming to rest. In most cases, however, the motor is commanded to move to the next step before it comes to a rest. Working principle of variable reluctance stepper and permanent magnet will be shown to see differences and similarities with hybrid step motor. Variable reluctance stepper, VR, as illustrated in the video, only one pair of teeth is aligned with the windings at any time. When the controller energizes a second pair of windings, the rotor turns so that different pair of teeth will be aligned. Because the teeth aren't magnetized, it doesn't matter whether the winding behaves as a north pole or a south pole. The controller has delivered current to the B and B windings, and the rotor has aligned itself accordingly. Now, the C and C apostrophe windings are energized. The C and C apostrophe windings attract the nearest pair of teeth, which moves the rotor 15 degrees clockwise. However, there's a problem. The torque of the VR stepper is so low that it can't turn significant load. For this reason, VR steppers are not commonly found in practical systems. In fact, I've only ever seen a handful of VR motors for sale. Permanent magnet stepper has permanent magnet rotor, which is driven by the stator windings. Stator windings create opposite polarity poles compared to the poles of the rotor, and the result is the movement of the rotor. A stepper motor is a polyphase AC synchronous motor, and it is ideally driven by sinusoidal current. There are 4 commonly used excitation modes for stepper motors: wave drive, full step, half step, and microstepping. These excitation modes have an effect on both the running properties and the torque that motor delivers. The wave drive method has been simplified to better illustrate the theory. In the illustration, each 90-degree turn is representing 1.8 degree of rotor rotation in an actual motor. In the wave drive method, also called the one-phase on method, only one phase is turned on at a time. When we energize the A phase, a south pole, it attracts the north pole of the rotor. We turn off A and turn on B. The rotor rotates 90 degrees, 1.8 degree of rotor rotation in an actual motor, and so on. Each time, only one phase is energized. The wave drive has 4-step electrical sequence to rotate the motor. Full step drive. Once again, in the illustration below, every 90 degrees represents 1.8 degree rotation in an actual motor. If both phases A and B are energized as south poles, the north pole of the rotor will be equally attracted to both poles and line up directly in the middle. In sequence, as the phases are energized, the rotor will rotate to line up between the 2 energized poles. Half-step drive. Half-stepping combines the 2 previous methods. In this case, we energize the A phase. The rotor lines up. At this point, we keep the A phase on and energize the B phase. Now, the rotor is equally attracted to both lines up in the middle. The rotor has rotated 45 degrees, 0.9 of rotor rotation in an actual motor, Now we turn off phase A but leave on phase B. The motor makes another step, and so on and so forth. By altering between one phase and onto two phases on, we have cut the step angle in half. Remember that with a smaller step angle, the vibration is reduced. Microstepping. Microstepping is a way to make small steps even smaller. The smaller the step, the higher the resolution and the better the vibration characteristics. In microstepping, a phase is not fully on or fully off, it's partially on. Sine waves are applied to both phase A and phase B. 90 degrees apart, 0.9 in a 5-phase stepper motor. When the maximum power is in phase A, phase B is at 0. The rotor will line up with phase A. As the current to phase A decreases, it is increasing to phase B. The rotor will take any tiny steps towards phase B until phase B is at its max and phase A is at 0. The process continues around the other phases and we now have microstepping. There are some problems associated with microstepping, mostly accuracy and torque. Because the phases are only partially energized, the motor torque is reduced, usually by about 30%. Also, because the torque differential between steps is so small, the motor sometimes cannot overcome the load. In those cases, the motor may be commanded to move 10 steps before it actually starts to move. Computer-controlled stepper motors are a type of motion control positioning system. They are typically digitally controlled as part of an open-loop system for use in the holding or positioning of applications. In the field of lasers and optics, they are frequently used in precision positioning equipment such as linear actuators, linear stagers, rotational stagers, goniometers, and mirror mounts. Other uses are in packaging machinery and positioning of valve pilot stages for fluid control systems. Commercially, stepper motors are used in floppy disk drives, flatbed scanners, computer printers, plotters, slot machines, image scanners, compact disk drives, intelligent lighting, camera lenses, CNC machines, and more recently in 3D printers.